All right, folks, I got some old school 311 going on. Check out these lyrics. Doesn't amaze me. Yeah, that was cool. Some old school 311 from the 90s. 6 protons, 6 neutrons, 6 electrons is encoded in this planet we live on. That's carbon, right? 6 protons, 6 neutrons, 6 electrons. We just got done talking about all of that. All right, cool stuff, folks. Okay, so I want to spend just a little bit of time talking about nucleosynthesis and the origin of the elements. All right. So this is really cool, and this is at the end of the chapter, so I'm kind of going a little backwards, but I just wanted to talk about this for 1 minute. So we have the Big Bang, or we theorize there was a Big Bang, right, which created everything. Okay. And we notice here 10 to the minus 10 seconds. That's like 1/10 billionth of a second. Protons, neutrons, and electrons started forming. Okay? And those protons, neutrons, and electrons were able to combine. So look at this chemical reaction. So this 11P and 10N, those are the chemical symbols for proton and neutron. So it's the same with the mass number on top and the atomic number on the bottom. A proton is just one single proton. So this 1 and 1 says it's just one proton. So I'm going to write that down. You should know those symbols, right? 11P equals proton. So 10N is neutron. The N for neutron, but we also know that it has to be a neutron because the 1 tells us there's 1 proton plus neutron. The 0 tells us there's 0 protons, so it's all a neutron. And then finally, when we say 0, let's see here. Let me rewrite that. We say 0 minus 1 E, and that's our symbol for electron. Okay. So now this proton and neutron combine to form what we call a deuteron. Okay, so that's the combination of a proton and neutron. And look, if you imagine, we know that our nuclei of atoms are made up of protons and neutrons. So this is really like how we first start to begin to create nuclei. Okay? And now, so what started happening is very quickly then after that, hydrogen and helium were able to form. Okay? So a very simple nuclei. But as it turns out, that's really where nucleosynthesis kind of cut off because there wasn't enough energy to keep fusing these hydrogen and helium into larger atoms. So this is why about 99% of the universe is hydrogen and helium only. Okay? Because once all this hydrogen and helium was created, all this material is getting flung out. Okay? And there was really not enough, pressure, gravity, energy, whatever you want to call it, to keep fusing these hydrogen and heliums together. Okay, so it wasn't for about another billion years later, between 300,000 and a billion years later, that atoms started to form through stellar nucleosynthesis. So in other words, all of these stars and galaxies started forming, mostly comprised of hydrogen and helium. And at that point, there was enough energy in those stars and star clusters to fuse heavier nuclei together. And so, for example, this is showing you, so this is an alpha particle, okay, which is the same thing as a helium nucleus, okay? And if you look at how these numbers work, right? 3 times 4 gives you 12. 3 times 2 gives you 6. So as these heavier nuclei were able to fuse, they were able to start creating the elements carbon and boron and oxygen and nitrogen, and eventually all the way up through iron, right? Iron 56, okay? So there was a huge lag in the evolution or the origin of the elements. And to this day, it's why 99% of the universe remains to be hydrogen and helium. Okay, so I'm going to move forward and get into the naming of compounds. So naming compounds is going to be a pretty major aspect of this course. So I'm only going to give you one lecture on naming compounds, but this is something we're going to be working on throughout the entire semester. So I want to make sure that you're making a good effort right away, a good initial strong effort to learn how to name compounds. Okay, so I'm going to go through this one by one and then summarize at the end. So naming, and all the naming we're going to do in this class is on inorganic compounds, okay? And I'll talk about that at the end. The difference between inorganic versus organic, okay? We're just focused on this for this class, okay? And so there's a couple different types. So the first we're going to focus on is covalent. So covalent is going to have a different naming scheme than ionic, okay? So binary molecular compounds, so binary, meaning compounds consisting of two, in this case non-metals, that makes them covalent, okay? So we first look, so for example, my example that I have is SO3. And the first thing we do, we look at the very first element, okay? And we just name it as is, sulfur, okay? Easy, okay? Just read it right off the periodic table, sulfur, all right? The second element name is changed by adding the suffix "ide." So for example, we note the second element is oxygen. Oxygen will become oxide. Okay? And then now we have to look at the quantity. Remember, respect the subscript. Okay, right? We look at the quantity right there, and we use prefixes to identify how many of those atoms are present. So 3 means tri, so it's sulfur trioxide. Okay? What if I had this one? Okay? Well, sulfur, and it's oxide, there's a 2 right there. 2 is di. So this would be sulfur dioxide. I'll give you another one, 2 examples that you already know. Okay? CO and CO2. Okay? And note, on the very first element name, okay, if there's only one of them present, we don't say mono. Okay? Here's this list, right? 1 is mono, 2 is di, 3 is tri, etc. But let me just back up for 1 second. We don't say monosulfur trioxide. So it is implied with the first element, no mono. Okay, only. So now what about these two? Carbon monoxide, monooxide. Okay, you can say carbon monoxide. You know carbon monoxide, the stuff that comes out of your tailpipe. Don't suck it in, right? Okay, what about CO2? Carbon dioxide. And sorry, I'm writing these all together. These are 2 words. Carbon dioxide, carbon monoxide. Okay, so let's go to this other example here, right? Okay. Do not use the prefix mono when naming the first element, like I just said. Okay. So 1, 2, 3, 4, 5, 6, 7, 8, 9, 10, 11, 12. We really won't even get much past like 7 or 8, to be honest. But here they all are. Okay. Mono, di, tri, tetra, penta, hexa, hepta, octa, nona, deca, undeca, dodeca. Yes, you have to know these. Yes. You have to know these. Make some flashcards. This is not going to be the only table in this list that I tell you have to know these, so you have to make a bunch of flashcards. Okay? Mono, di, tri, tetra, penta, hexa, hepta, octa, nona, deca, undeca, dodeca. Okay? So prefixes ending with O or A are modified when used with elements beginning with vowels. Okay? So for example, we note that deca, right, is D-E-C-A, but what about when used with oxide? It's not decaoxide, it's just decoxide. okay? Or same with the carbon monoxide. It wasn't monooxide, it was just monoxide, okay? So if you have O or A, you modify those with elements that begin with vowels. So oxygen is a good example of that, okay? So P4O10, and look, now there's 4 on this phosphorus. So 4 is tetra, so tetraphosphorus decoxide, okay? Let's keep going. There's going to be lots and lots of examples for you to work on with these. Okay, so that was covalent compounds. Here comes ionic compounds, okay? Ionic compounds. So binary ionic compounds consisting of a cation, which is usually a metal, and an anion, usually a nonmetal. Remember, we talked about that in the previous lecture. Ionic compounds are metals and nonmetals, or in other words, the leftmost side of the periodic table combined with the rightmost side of the periodic table. And so when we write these, it's order specific. So it's always going to be cation first, anion second. Always cation, anion. Okay? The cation, you just name it straight up. Magnesium, sodium, whatever, right? No changing the name. No dies, tries, penta, none of that. You don't do any of that in ionic compounds. Okay, this list, covalent only. Okay, tattoo that on your forehead. Covalent only for these prefixes. Okay? So let's go back to ionic compounds. Cation, anion. Cation first, anion second. Cation is just straight the name, magnesium. The anion, we put an "ide" at the end also. So that was similar to what we did with the covalent. Okay? We put an "ide" at the end. So chlorine would become chloride. Bromine would become bromide. Even oxygen can form covalent compounds, but oxygen can also form ionic compounds. Oxygen also, similarly, just like we did before, oxide. Okay? So formulas for ionic compounds must always be neutral. So we talked about how magnesium, it's one of the elements in group 2. Okay, let's just fast forward to my periodic table. Right, look, there's magnesium. Look, it's in this row where things are always 2+. This row, things are always 1+. Okay? So we have to know that. There's going to be nothing in the formula that tells us about magnesium being +2. We just have to know that it's +2 from the periodic table. Okay? And we also know from the periodic table that the halogens are always -1. So there has to be, we'll say 2 times 1 minus. It has to be neutral. In other words, the charges have to add up to 0. Okay? So in ionic compounds, we're just going to say the name of this compound. The name of this compound, MgCl2, it's just magnesium oxide, or excuse me, magnesium chloride is the name of this compound. That's it, magnesium chloride. There's no di, tri, tetra, etc. with the covalent compounds. So ionic compounds are a little tricky because we have to recognize, like if someone just says magnesium chloride, so suppose someone just tells you the name, you have to be able to work backwards to figure out that it's MgCl2. If somebody tells you that it's MgCl2, you have to also be able to work forwards that it's magnesium chloride. So be able to go back and forth, okay? And so that means you're going to want to know all of this stuff, all these charges, right? I circled the red. The red charges you should know, because that's how you're going to know how to make compounds out of it. I mean, look, there's Mg2+, there's Cl-, so we have to have 2 of these chlorines for every 1 magnesium to make an ionic compound out of it, okay? So let's keep going, okay? And let's talk about the transition metals, okay? So transition metals, right, that region in the middle, they are variable. Their charges aren't always set. Like, for example, here we can see iron comes in 2 forms, 2+ or 3+, okay? So For metals that form cations with different charges, so that's transition metals, a Roman numeral is used to indicate the charge of the cation. So for example, if I have FeCl2, okay, we have to do a little bit of math to figure out the correct name. We know that chlorine becomes chloride, which is 1 minus, okay? And if I have 2 of those, right, if I have 2 chlorines, that means I have 2 minuses, okay? So that means my iron has to be 2 plus, okay? And that's going to give me iron 2 chloride. So I would actually read this by, phonetically by saying iron 2 chloride. And that 2 tells me the charge on iron is 2 plus, which tells me I need 2 of these Cl minuses. Okay? So there's something I want to address right away too. Okay, look, when I'm going to write this, 2 Cl minuses does not equal this. Nope. Don't do it. 2 Cl minuses does also not equal this. No. Big no. Okay. But 2 Cl minuses, 2 Cl minuses definitely equals this. 1 Cl minus and another Cl minus. Respect the subscript, okay? And so when I have this 2 down here, what it actually means is I've got an FeCl and an FeCl, right? I've got 2 chlorines bonded to this iron. So keep track of all of that, because some of you are going to screw it up, and that's okay. You're learning, you're beginning. But keep track of this. 2 Cl minuses does absolutely not equal Cl2 minus, okay? 2 Cl minuses absolutely does not equal Cl raised 2 minus. But 2 Cl minus definitely does just equal 2 individual Cl minuses, okay? And then when I allow them to bond with an iron 2 plus, this is what happens, okay? Or iron 3 chloride. So we recognize that we would have 3 single chlorides. So I would have to have an iron charge of 3 plus to give me iron 3 chloride, okay? So keep that in mind. Look, there's copper 1 and copper 2. There's manganese 2 and manganese 4. There's vanadium 3 and vanadium 5. So we kind of have to use information about our formula to know what charge we have. So for example, suppose I gave you this formula right here, VCl5, and I asked you to name the compound, okay? So we look at this and we recognize that chlorines are always -1, and there has to be 5 of them. So this has to be vanadium, and don't write out the word 5. This was my phonetic. It's vanadium 5 chloride, okay? Okay, I'm going to move forward. I know I'm going through each one of these quick, okay? So make sure that you're practicing, and I'll point out resources of where you can practice, okay? So here's just that same info that I showed you, but just now with a table. And you don't have to memorize this because the transition metals are all variable. You never know which flavor you're going to have unless you see it bonded to something. Then you know what you have. So for example, if you have iron with 3 chlorines, you know it has to be iron 3. But if, for example, you see iron with only 2 chlorines, you know it has to be iron 2, okay? So don't memorize things when you don't have to. And here's just kind of a list so you can connect how this all works, okay? And no, this is not a full list at all. These are just some of them, okay?